Every program you run on Linux, every browser tab, every background service is a process. And each one follows the same lifecycle from the instant it's created to the moment the kernel reclaims its resources. Let's walk through that entire journey. A process is not the program file sitting on your disk. It's a running instance of that program with its own memory, its own file descriptors, its own PID. Think of the difference between a recipe and someone actually cooking from it. Two people can follow the same recipe and produce separate meals. You can launch the same program 5 times and get 5 distinct processes. The kernel tracks every one of them using a data structure called the task struct, which stores everything from the process registers to its open files. Creating a Linux process happens in 2 stages. First, an existing process calls fork, which makes a nearly exact copy of itself. That copy, the child gets a new PID, but inherits the parent's memory, file descriptors, and environment variables. Then the child typically calls exec, which replaces its own memory with a completely different program. The parent's code and data get wiped in the child and swapped for whatever binary you actually wanted to run. This forked and exec pattern is how every process on your system was created all the way back to PID1. At any given moment, a process lives in one of 4 states. Running means it's either executing instructions on a CPU right now or sitting in the run queue waiting for its turn. Sleeping is the most common state by far. The process is blocked on disk I/O, a network response, a timer, or just waiting for input. Stopped means a signal like SIGSTOP has frozen it, usually from pressing Ctrl-Z in a terminal. And zombie, that's the interesting one. The process has finished executing, but its exit status hasn't been collected by the parent yet. The kernel holds a small record so the parent can read how the child ended. Here's fork and exec in actual C code. The parent calls fork, and from that point, 2 copies of this program are running. The return value tells them apart. The parent receives the child's PID, and the child gets 0. That's why you see this if-else branch. In the child path, we build an argument list and call execvp to run ls with the dash of flag. The child's original memory gets replaced entirely. The parent path calls waitbid, which blocks until the child finishes. That wait call is what collects the child's exit status and prevents the zombie from lingering. A process dies in 2 ways. It can call exit on its own, returning a status code to the kernel. 0 typically means success. Anything else signals an error. Or it can be terminated by a signal from another process or the kernel itself. SIGTERM is the polite approach. It asks the process to shut down, and well-written programs catch it, run their cleanup code, and exit gracefully. SIG is the last resort. The kernel terminates the process immediately with no chance to clean up. After death either way, the kernel frees the process's memory, closes its file descriptors, and marks it as a zombie so the parent can read the exit status. A zombie is a process that has finished running but whose parent hasn't called wait yet. It holds almost no resources, just a tiny entry in the process table. Under normal conditions, this lasts only milliseconds. But if a parent is buggy and never calls wait, zombies can accumulate and eventually exhaust the process table. Orphans are the opposite situation. The child is still running, but the parent has already exited. Linux handles this by reparenting orphans to PID1, which is init or modernly systemd. PID1 always calls wait, so orphans get cleaned up reliably. This design means the kernel never has to guess who's responsible for collecting a dead process. That's the full lifecycle. Fork, exec, run, exit, get reaped. Every process on your Linux machine follows the same arc. Thanks for watching Awesome Linux TV. Thanks.